About last time, I had several follow-up items, and the first is I claimed an embedding of this group in G2 of K, where K is a field. It's not 2, and I think there were a lot of mistakes I made, actually, so I've been writing this up more carefully, and I hope you won't suffer so much when I complete it. I'll send a copy to Professor Vavilov maybe in the next day or two. So if you didn't understand everything, then it's not your fault. Okay. Second, last time we discussed embeddings.
So this is also a non-split extension?
Yes. Now, the proof that it's non-split is an additional thing that has to be proved. But I wasn't attempting to prove that last time. So, but I've written quite a bit on that subject. So
one and only one non-split extension.
That is a theorem, yes. Okay.
And not a trivial theorem.
It's not too.
Small lemmas.
It's not too difficult. Yeah, I think the first proof was due to Donald Higman when he studied flag transitive subgroups of GLN, and then this was a case that came up. Okay. All right. Embeddings of finite groups and exceptional algebraic groups. Last time I gave a list, and I made some comments on special cases, and I want to call attention to the paper by Alex Riba called Short Proofs of Embeddings in Exceptional Algebraic Groups. And you may remember that last time I discussed, PSU 3.8. That's a subgroup of E7 over the complex numbers. And this was proved by Alex Riba and myself. And it was actually a rather long paper, and we were very pleased with ourselves. Well, in this short paper, here's what Alex Riba accomplishes. So in this paper, there are about 4 pages of lemmas. They're all completely elementary linear algebra, where about a G, a finite group, and V, a module, and G subspaces, let's say W, of K is a field of characteristic not 2 in this part of the discussion. Now this is a Lie algebra. The endomorphism ring of any finite dimensional vector space is naturally a Lie algebra called little GL. And a subspace W, a linear subspace, which is a G module, could be closed under the bracket and be a submodule. Gives conditions. For W to be a Lie subalgebra. And some of these, they're really kind of simple. Maybe we could all think of them ourselves, but others are not very obvious, but they're easy to check. So let me just say what he did. So this, I'll say these are elementary. Oh, and let me keep track of the time. It's about 3:30, so you'll give me 50 minutes or 55 minutes? Okay. All right. Okay, so let's take the case where G is PSU 38. And the character table is available. That's in the Atlas of Finite Groups. If you don't know about this, this is a very large book compiled about 30 years ago. And it's really nice to have all that information in one place. It's about subgroups and irreducibles, automorphism groups, and so forth. So Alex found out the following. Oh, he found, let's see, where did I write it? Um, 56 means the unique irreducible representation of dimension 56. I think you'll catch on to the notations. 133 sub A, 133 sub B, 133 sub C means the irreducible representations of dimension 133, and there'll be some other numbers that come up. Okay, but now the point is that I'm going to write down a bunch of statements. All you have to do is compute inner products, the orthogonality relations for finite groups, to get the following statements, which probably you couldn't do in your sleep, but maybe you can. The exterior square of 56 is 1 plus 513a plus 513b plus 513c. And so by lemma 3, now just for reasons of time, I'm not proving these. A proof of any one of these lemmas just takes a couple of minutes, really, but says that the symmetric square of 56 has a G invariant Lie algebra structure on it, and S squared 56 as a direct sum of irreducibles looks like 133a plus 133b plus 133c plus 16 more, which I won't try to write down, of degree. Degree is bigger than 133. So that's a pretty long calculation. Of course, it's completely straightforward. Oops. All right, let's try this way. And the only common irreducible in these decompositions is 133 sub A. So 133 sub A has a G invariant Lie algebra structure. And other lemmas in that list of elementary ones imply that this is a simple Lie algebra. And the classification implies this is the Lie algebra of type E7. So that's a really short proof, and all you have to do is compute a bunch of inner products. Of course, you have to have the insight to see something like this, but that is a rather amazing shortening of the original proof. So I do want to call your attention to this paper, and I will leave a copy of this here before I go.
So you're suggesting that just by looking at the character table, you can guess which one might be?
Well, if you have fantastic insight, you can. Yeah, but once you point to the way to do it, it's easy. And I mean, these lemmas are suitable for a student seminar. I think they're really pretty simple. So if only you know where to look, there's a nice proof. Okay, so I wanted to call your attention to that. Okay. Now, I wanted to give a very short introduction to vertex algebra theory. And remember last time, if V is a finitely generated vertex operator algebra, there's a theorem that says the automorphism group of V is an algebraic group. So that's something relevant to
Sorry,
the...
if I may interrupt.
Yes.
In this proof, S256 has a gene variant V algebra and then...
That follows from these elementary lemmas.
Right.
Well, I'm sorry, I don't have time to prove this. This follows...
I'm just asking the logic. There are three of them. Is that the point? 133 plus 133 plus 133, or just one of them is what is involved in the proof? You know, there are three of them. 133 plus 133 plus 133.
Yes.
Is the three of them the point, or one of them is the point?
One of them is the point. We're looking for...
The other ones play no role.
Except in the calculations, yes.
And to give a Lie algebraic structure, you have to multiply 133 with 133.
We have to study these lemmas, yeah. Okay. Now, so let me, now, I mean, to give all the definitions and discuss it carefully would take about half an hour, so I'm just going to mention a few highlights. First of all, V is a graded space, and N can be run over any additive subgroup of the additive group of the complex numbers, but here...
The sum of VNs. Yeah.
Vn, thank you. Here, N runs over the integers, and in almost every case there are no negative terms. So that's the restriction I want to use. Secondly, dimension of Vn is finite for all n. And third, there exists an element 1 in V0, and 1 is called the vacuum. This terminology comes from physics, and there exists, an element omega in V sub 2, and omega is called the Virasoro element. and which have the following property, well, which have properties that I will list in a few moments. I should have done this in a different order. Okay, there exists a linear transformation y from V to the following algebra. This would be a two-sided power series.
What is two-sided power series?
Well,
That's not a ring. It's a formal thing. Yeah?
It's not associative, but
What?
I didn't say it was a ring. It's just a linear space.
Yeah. Okay.
Okay. For two elements of this, it may be possible to multiply them, but in general, no. Okay. So if V is in V...
So it's not Laurent series, it's also infinite to the negative direction.
Yes, that's right. So Y of V Z looks like the following: V sub n, Z to the power minus n minus 1, where V sub n is an endomorphism of V. Okay. And Y of the vacuum element is just the identity on V, and that really is a two-sided series. It's 1 at Z to the power 0, and all the coefficients at the other powers of Z are 0. And when you apply it to the Virasoro element, you get this. And now I shift the indexing and the Ln satisfy the Virasoro commutator relations, which look like this. Plus, now let me get this right, Kronecker delta m plus n 0 C m cubed minus m over 12 times the identity on V. And C is a scalar, and it's called the rank. Okay, now, you know, these properties go on and on. When I first saw this, I said, is this really, why can't you make it 1? If you studied Virasoro algebras, you know, this is a central extension of it. You can change the basis slightly to make this equal to 1, or any other number you want. But should you? Well, it turns out that when they come up in this context, things are a little bit more rigid, and you can't change it. And so this number has something to do with background for the particular vertex operator algebra you're talking about. I'll give an example of this shortly. Okay, now what else do I want? And there's something that's kind of like a Jacobi identity but there are singularities and all kinds of formal things that have to be very carefully stated. But I think I can stop right around there. Okay, now a vertex algebra.
What is the difference between summation omega n and summation ln?
I'm sorry, what's the difference?
Yeah.
Well, I just define this to be, let's see, is that right? Yes.
Yeah, but then you haven't shifted the power of z.
Well, I just put it in different, what do you mean?
It's the same power of z that you have in the expression for
Minus n minus 1 and minus n and minus 2.
minus 2.
That just makes the algebra work out better. So okay. Vertex algebra, the coefficients form a commutative ring. Okay, so it could be the real numbers, or it could be the integers mod p, just a general commutative ring. We require a vacuum element that has this property, but we don't require a Virasoro element. Let's see, how do I say this? No, I think I'll just leave that off. Now, in a vertex operator algebra, V over the complex numbers, we might have an integral form. For finite dimensional algebras, in characteristic 0, you know definition of integral form. So it is J, where Jn is an integral form of the vector space Vn. 1 is in J0. J is closed under all products. I defined this last time, but I guess I didn't do it this time. Okay, there exists a product the kth product, and it's defined this way. V star n, k of W is V sub k applied to W. V is in V. V sub k is an endomorphism of V. That comes from the series, the double-sided series. So you can apply an endomorphism of V to an element of V. So that gives you a product structure. Okay. So J would be closed under all these products. 1 is in J0, and we also want the following. There exists a positive integer m, so that m times omega is in J. And omega is the Virasoro element of the vertex operator algebra V. Okay, So it's just the sort of thing you'd expect, a kind of an integer version where the z rank of this is equal to the dimension of the space Vn. It's closed under all the products, and it has a vacuum. Okay. Okay, now a few quick observations. Well, first the definition. Has this vertex operator algebra has CFT type, conformal field theory type, if and only if. The negative terms are 0. And V0 is only one-dimensional, so it's spanned by the vacuum element. The vacuum element lies in degree 0. And degree 0 could be bigger, but this is a requirement for conformal field theory type. And I think almost all the examples I'm going to talk about satisfy this. This is the most popular kind of VOA for the representation theorists. Okay, now for V of CFT type, V1 under the zeroth product is a Lie algebra. Amazing. You've got this very complicated infinite dimensional graded space and an infinite number of products going on, but we get something that's very familiar. And I won't prove this. This is, you can, some good references. The book of Frankel, Lapowski, Merman. And Borchard's original paper, which is kind of tough to read, but it has a lot of good ideas there. Okay, and as I mentioned last time, if you take an element in degree 1, you've got this operator A sub 0 and this is a derivation for each algebra V with the kth product. And the proof of that is just formal playing with the axioms. And it's difficult to write it out because it's fairly technical. But now, because all the VNs are finite dimensional in characteristic 0, this endomorphism is locally finite, and it's a derivation, so you can exponentiate it and get an automorphism. Can get automorphism of V by taking exp of A sub 0. Okay, now let me define this. It's pretty obvious what it should be, but let me write it down. Oh, I've got an empty board. How nice. V vertex operator algebra. G in and V is an automorphism of the VOA if it's invertible. G takes the vacuum to the vacuum, and G takes omega to omega, and G preserves all the products. And that means just what you think. If you have A, B, and V, and K an integer, then G of the kth product of A and B should be the kth product of GA and GB. Okay, and the set of such forms a group. It's pretty obvious.
Should it preserve grading?
Yes, but that's a consequence of,
Okay.
Well, I mean, a property of L0 is that its n eigenspace is V sub n. That's not obvious. But so given that G preserves omega, it'll preserve all the components of omega in the series. So it preserves all the LMs, and so it preserves their eigenspaces if they have eigenspaces. So, and I mean, there are a lot of formal things that were explored over the decades. There are families of spaces where you can have a fixed vacuum, but a whole family of elements that are candidates for being a Virasoro element and things of this sort. Anyway, we fix these things today. We don't change anything. Okay. So that's an automorphism. And I want to talk about a particular family of VOAs, and these are called lattice VOAs. Now, when you look at the literature, it's very difficult to prove that a candidate for VOA actually is, because these properties are really fairly technical. But this is one of the most pleasant families to work with. So let me explain how that goes. Suppose L is a positive definite integral lattice. Okay, now what that means is L looks like z to the n as an abelian group. And there exists a symmetric positive definite bilinear form. Okay, so that's a lattice, and we also want the property that L is even, and that means that XX is an even integer for all x in L. And you know examples of these. If L is a root lattice of type A, D, or E, it's an even integral lattice. Think of the Cartan matrix. Okay. work. Let me pause for questions. Let me know if you have any questions. Do you have a question?
And what if it is root let is not of type AD but of some other types?
Not even.
It's not even.
Well, for those types, the Cartan matrix isn't even symmetric.
Symmetric. It's even but not symmetric.
But I can say something about those cases. But step one is to talk about the nice cases, and then I can get a corollary. Okay. Okay. So here's the lattice VOA based on L, an even lattice. An even integral lattice. And I don't assume it's a root lattice, but that will be a case later. So, okay, so here's what we do. Oh, I'm sorry. That is V as a vector space. And this is just the group algebra of L. And the usual way to write a basis is like this with exponential notation. Again, this comes from physics or functional analysis. You can think of this as a function. You apply it to a vector, and you get the scalar e to the power alpha dot that vector. So, okay. Now, what's this? Well, we let H be the complex vector space which contains L. And T is an indeterminate. And H sub minus n is T to the minus n tensored with H. Now maybe that bothers you a great deal. It's you can think of these all as subspaces of
TT.
beg pardon? Oh, sorry, T. Thank you.
What's S?
Well, I'm going to explain.
Okay.
S is the symmetric algebra, polynomial algebra. S on this infinite direct sum. And excuse me, I'm very ignorant of physics, but I can mention a term. This is Fock space. Okay, now V is supposed to be graded. So I have to tell you about the grading. Okay, V is a tensor product of graded spaces. And for S, the degree of H sub minus K is K. Okay, so for example, the degree of this monomial see, I hope I get this right. 3 plus 8 is 11, 16. Okay. And in the group algebra component, E upper alpha has degree 1/2 the inner product of alpha with itself. This number is an even integer, so I divide by 2 and I get an integer. Okay. Now the hardest part of the story is to describe y. That's the vertex operator. That's what tells you how to assign to an element a two-sided power series. And well, that's hard. I'll say only a little bit, and it's very carefully discussed in that book. Where did I write it? Well, somewhere up there. Yeah. Oh, it's your friend, Igor Frankel.
Yes.
Yeah.
Well, I have the book.
Good. Okay. I'll just say for the case, just this one case. Well, actually, it's one. Right. It's the constant polynomial 1, right? Tensored with E upper alpha. Y involves factors of the form exponential of sum n less than 0. Let me get this right. Alpha of n, z to the minus n minus 1 over n factorial. I probably have a sign wrong here someplace. And if n is less than 0, alpha of minus n is a creator. And if n is bigger than 0, alpha of n is an annihilator. And there are some other things as well, but this, so if you create an infinite number of terms, you can't really sum them, but if you assign different degrees to each of the pieces, then that does make sense. And so think of these things operating on the S part of this tensor product. This one acting as multiplying by a variable, and this one is taking a partial derivative.
And factorial.
Yeah. Thank you. No, -1. Sorry. Okay. Anyway, all these formulas are in the book, Frankel, Lepowski, Merman. And if I take a polynomial expression in here, it really is really quite messy. You have to deal with things called normal orderings. If you can't create too many things before you start annihilating them, or you have undefined sums. But if you create a bit and then annihilate, then you can add more things. Okay, so sorry this is so complicated. Okay, let us now take the case. Let's say V is of lattice type. And let's look at degree 0. Well, this can only be the span of the constant polynomial 1 tensored with E upper 0, the 0 element of the lattice. The degree of this tensor product would be this degree plus this degree, and you have to have degree 0. Okay, so the next step is V1, and that, how can you get a non-trivial polynomial expression of degree 1? And the answer is, that's the only way. Just linear expressions, degree 1 monomials from the degree 1 copy of H only. And then here, we have a sum E upper alpha, where the self-inner product of alpha is 2. In other words, it's a root. A lattice may not have a root, but a root lattice will have a root, right? So if L is ADE root lattice, then this has dimension equal to rank of L plus the number of roots. And that's the dimension of the Lie algebra of respective type, ADE. Okay. So I claimed that we get a Lie algebra in degree 0, and here you see it dissected a little bit. Okay. Okay, now.
Somehow sub-relations are encoded in this Y, right?
The which?
Sub-relations on the algebra elements.
Third relations.
Because you construct your algebra just from, well, Cartan matrix to say.
Yes, that's true. Well, I don't know exactly what you mean by encoded, but yeah, it's just this standard way of writing the simple Lie algebra with a Chevalier basis. Okay, I want to talk now about integral forms. I gave a definition for an integral form in a VOA, but for a Lie algebra, which is simple, finite dimensional over the complex numbers, we have the z-span of a Chevalier basis. If you take the product of any two members of a Chevalier basis, you get an integer linear combination of members of the Chevalier basis. Oops. Okay, But now let's go. Let's say L is type ADE, root lattice. Then there is a standard integral form. And this was described in a paper of Chongying Dong and myself. And it turns out that it was mentioned by Borchards many years before that, but it wasn't published, or he didn't give all proofs. I can't remember exactly, but anyway, here's a good way to describe it. Take the components of y of e upper alpha z applied to the vacuum vector for all alpha in L. So L is the root lattice of type ADE. This is a series where the components are operators. Apply those operators to the vacuum vector, and then you get actual vectors at each power of z. Collect those all together, and this set generates an integral form. Or another way to say that is, if you take the vertex algebra, not over the field but over the integers, the subvertex algebra of V generated by that set, that's an integral form. Okay, so let's call it J. Then look at J intersected with the degree 1 piece. Now that's our familiar Lie algebra. And what you get is exactly the lattice spanned by the Chevalley basis. It's exactly what you expect. So this is a precise generalization of Chevalley basis. Okay, it is Chevalley lattice.
Chevalley basis is unique up to automorphism?
Yes, I believe, yes. Yes.
One has to worry about some fundamental groups and so on.
Okay.
It's not totally unique.
I'm sorry?
Up to some constant.
The toral part is not just
Chevalley basis is not totally canonical.
the Chevalley base, the
Some
Chevalley
construct Chevalley
system.
basis for simply connected groups, some construct for the adjoint group.
Chevalley system is canonical. Chevalley system, the E alphas.
But given a Lie algebra over J, one can ask whether it's unique or not unique.
It's not unique. H alphas are not unique because
Lie algebra, not alpha.
But maybe it's just if you rescale your one, then you get another one.
But that would be isomorphic. So I'm saying whether a Chevalley Lie algebra is unique up to isomorphic.
No,
I am sure it's not.
no, it's not.
So there is more than scaling involved.
No,
This is another paper. We refer to.
no, it's a different question. So you can take other basis, but it's algebra.
I just said, there is just not simply connected and adjoint. But I think there is more than that.
No, sits
By
inside,
definition,
outside sits inside C, well, possibility.
Lie algebra over Z. I'm asking whether the Chevalier form of that Lie algebra is canonical. Up to isomorphism, it's
Well, up to Z, isomorphism is canonical.
no, but as I said, you have to worry about simply connected versus adjoint. They certainly are not isomorphic.
by definition, I think Chevalier algebra is a Lie algebra of simply connected.
Which I think depends on the convention. Chevalier algebra, I think, is maybe for the adjoint.
Yes,
How to do?
that's true. Maybe here we get simply okay, one of
Okay.
We are worried whether your definition of Chevalier lattice is the Lie algebra or of the adjoint algebraic group or simply connected algebraic group.
Adjoint.
Okay.
Because it lives in V1. V1's a Lie algebra.
So there is
So
that difference.
That defines the embedding.
Yeah, so, but you could have also taken it in simply connected group. That will define you a different Chevalier lattice. For each representation, you will have another lattice.
Well, depending on the lattice of weights.
Yeah.
Okay. Anyway, we have this particular integral form. So given J and K, a commutative ring, can get a vertex algebra over K by tensoring, right? It's and what about Chevalier group? Well, it works perfectly well because the standard let's see, how do I say this? Exponential map, I've forgotten what it's called, on the Chevalier lattice, sorry, for add E upper alpha, leaves the Chevalier lattice invariant. It's part of Chevalier's basic theory. But furthermore, if you study the proof, the action of, okay, similarly, the action of E upper alpha sub 0 leaves J invariant. And exp E alpha 0 also leaves J invariant. So that means you can define exp T E upper alpha on C of T tensor J. T is a variable. And so we get exp. Yeah, how do I put this? T Yeah, what I'm trying to say, maybe not very well, is that the proof of Chevalier that works for the Lie algebras can be copied with almost without any change. It's completely formal. So we get an action of the Chevalier group. If phi is the root system, on K, tensor J, and the theorem of Ching-Hung Lam and myself is if K is a field, this is most of the automorphism group of this vertex algebra. And more precisely what it is the action of this extended upwards by diagonal automorphisms and graph automorphisms. Not field automorphisms, because you're supposed to commute with the action of the scalars when you're acting on an algebra, right? Okay, so it's G phi of K extended by diagonal and field.
And graph. Not field.
Oh, sorry, graph.
No field.
Thank you.
Well, we use a different definition of Chevalier groups. For us, what you defined is the elementary Chevalier group.
Oh, okay.
And of course, Chevalier himself, he included part of the diagonal that corresponds to the root lattice inside his Chevalier group. He also defined H, the diagonal things.
Okay, okay.
So,
Well, I misremembered his paper then.
no, Chevalier defined, because Chevalier constructed simple algebraic groups, not simple abstract groups. So his groups had to be algebraic. So he spent the thing not just by the exponents of the unipotent guys, but also by some toral things.
Okay. Okay. I have a few precious moments left. Now, what about these others? Oh, I have another blackboard. For types B, C, G, and F, just take fixed points sub VA of graph automorphisms. So that maybe answers your question. Maybe not. So that is a construction of these types. And for twisted, what's the word? And so if we use graph times field, we get other vertex algebras whose automorphism group are the Steinberg groups. So
Steinberg groups in the sense of twisted Chevalier groups, not of the Steinberg.
yeah, this, this, and there's that theorem has an analog here. The full automorphism group is essentially these groups extended upwards by diagonal transformations. We don't have a theorem involving the Suzuki groups, the regroups, so that's something that I've wondered about. I think I'm about out of time. So.
Thank you very much. Are there any questions?
So what was that last comment in the bracket about Rie and Suzuki groups?
Yes. I would like to find vertex algebras whose full automorphism group is essentially this, and this, and this, and we haven't found any.
Any further?
So we have some kind of representations, right? For V1 acts on each VK by derivations, you said, right? So what are the other? So the first one is adjoint just representation, and what are the other representations in these constructions?
I'm sorry, I don't follow.
We have V1. You said that if A from V1, that A0 acts on each VK by derivations.
Yes.
And so we have some representations.
Oh, yeah, yeah.
And what are these representations in the construction? At least dimensions or whatever.
I can work that out in small degrees in many cases, but I don't know a general theory.
Pattern, yeah.
No, I think there is a pattern, but I don't know. I don't have a good answer for you. I'm sorry.
But you only have the only case that is realized this way are adjoint groups, yes? Or am I mistaken?
Well,
With this.
well, I think we can get other forms by doing this. This is the quotient of the dual lattice by the lattice.
Yeah.
Irreducible modules. VOAs have irreducible modules. They have a representation theory. And if you take our theory of the lattice and extend it to cosets of L in its dual, I believe you can get an action of this group.
Yeah.
So I didn't do it, but I think it's probably straightforward.
No, but I mean the construction itself just gives for the lattice VOAs just gives adjoint.
Well, no, if you introduce these other cosets, I think you can. I think it'll work. Give you possibly central extensions. Yeah.
Is it known what happens if one starts with an indefinite lattice?
Well, yeah. Then if you take, if you say how many vectors are there of norm 4, for example, it could be an infinite number in an indefinite lattice, and so those VNs would be infinite dimensional. You can still define it, but then it's harder to prove theorems when it's infinite dimensional. And there is some literature on studying those, but I've stuck only to the case positive definite.
Okay, any further questions? Let's thank the speaker again.